So today we're going to talk about similar triangles. Similar triangles are not the same as congruent. They have the same shape but not the same size. Remember, in congruent they must have the same size and shape. And the symbol we use for this is just a wiggly line, not an equal sign there. And in similar triangles, corresponding angles are congruent and corresponding sides are proportional. So let me draw two triangles here and put some labels on them. This triangle ABC, and we'll call the smaller triangle DEF. So we can say that triangle ABC is similar, I'm running out of room over here, sorry, to triangle DEF. So corresponding parts, now you're going to see this, I'm not sure if we talked about this yet. One arc means that those angles are congruent. Two arcs would mean that those two are congruent to each other. So if the two are, then the third one would have to be. Also with marks on them, you can put one mark for sides that are going to be congruent. In this case, we wouldn't be using these marks, but if they were congruent, we could put one mark on them like that and two hash marks if they're congruent to something else. So in solving, we can set this up then and use this idea. So let me say that this side is 16 meters. And this side is 18 meters. And in this triangle, we know this side is 6 meters, and I want to find this one. So I would set up a proportion. Now, there's lots of ways to do this, but I like to look at the triangle that has the variable, which is this small one right here, and I like to write my ratio from this. So x over 6 or 6 over x. That part doesn't matter. But this next part matters, and this is why the angle marks are marked. What corresponds to the x? Well, it's the one with two arcs, and this would actually have three arcs, as would this one, but if I mark them in there, I don't have much room. So it is the 18 would be the corresponding side, and what corresponds to the 6? The 16. Once you get that set up, you use your cross products. I don't have much room here, but hopefully we can get it in. 16x equal 108, and you divide, and you're going to get x equals 6.75. Please make sure you label, in this case, meters. So we would be done with that when we use the idea that these two triangles are similar. Alright, so we need to draw in this triangle. It's got a triangle inside a triangle. Okay, so we have our right angle here, we also have a right angle here, and they both have this side or this angle in common. So this is 20 meters on this side, this is 6 meters here, this is 5 meters here, and this total distance down here is the x I want to find. So again, the big triangle is the one I want to look at first, because it's the x, so we can put x over 20. Then in the little triangle, what corresponds to the x? Well, it would be the 5, and what corresponds to the 20? It would be the 6. Once you get it set up, you just use your cross products. 6x equal 100. Divide and you get x equals, I'm going to just round it to the nearest tenth, 16.7 meters. Questions on that? Now there are times when you might have to turn, do another one down here maybe, a triangle to get it to match up, and let's say we have 5 meters and 2 meters. I'm telling you that these two are similar, so we know that. There's the arc on that one. So again, oops, sorry, this is supposed to be an x here. I already gave you the answer, but so we put x over 5. The part I wanted you to get here is what do we need to do to these triangles? Well, we kind of flip this triangle and flip it over to make it correspond, so that the 8 does correspond with the x and the 20 corresponds here. And then when you do your cross product, you get 20x equal 40, and you do get the x equals 2 meters. So sometimes you might either need to rotate it or turn it or flip it or whatever. Which kind of leads us into our next thing, which is transformations, just a review of transformations. So transformations are just moving things around of geometric figures. So we have a reflection, which is just flipped over a line. That's what I was talking about there. If we have a shape and here is the line, if we want to reflect it over, then it's going to come over here and look like this. So a reflection, you know, a reflection from a mirror, it's not a very good drawing, but Translation is where you just slide it in any direction. So you take a figure and you just slide it. Rotation is a turn, and a dilation is where it's either enlarged, like you grab the corners and pull it out, or it's reduced and shrunken down. So those are different forms of transformations. So if we think about that, what happens to the area of a figure if it is reflected? So you have a shape of some sort, and you reflect it over an axis. What's going to happen to its area? Well, its area will stay the same, so it'll be the same. What happens to that area if it's translated? So let's say we slide it over somewhere. What happens to the area? It would stay the same. What happens to the area if it's turned? So if we take this and we turn it, what happens to its area? It stays the same. What happens to the area of a figure if it's dilated? Well, it depends. It is going to change depending upon if you're going smaller or larger. So if it's dilated, it could go either way. So that's the only one that changes among these transformations.